Hi, everybody. Thanks for joining us for this session on gamma ray bursts at the Chandra Frontiers in Time Domain Science. This is our second session of the day. The remaining sessions for this week will happen on Thursday, where we have 3 sessions on X-ray binaries, starting at 8 a.m. Eastern Time on Thursday. Our first speaker of this session on gamma ray bursts is Eleonora Troja from the University of Maryland and NASA-Goddard Space Flight Center, who will talk to us about gamma ray bursts. Can you start sharing your slides, please? And make sure to unmute yourself.
Yeah, I'm trying. Sorry, I couldn't find the Zoom window.
No worries.
Okay. So let me see. Okay. Oh no. So I will. Sorry, I keep losing the Zoom window. Okay, so I will start with the presentation. Sorry if you cannot see me, but I cannot turn on my camera. I don't know how to do it yet. So I was asked to introduce the topic of gamma ray bursts today, and I decided to focus in the to the multi-messenger era that has been giving us so many results in recent years. So just to start, for who is not familiar with gamma ray burst, these are some basic facts. You see the first plot on your left is the bimodal distribution of durations. So it's very well known that gamma ray bursts are divided in at least 2 classes. The one that you see in red are the one lasting for a few tenths of seconds, the so-called long duration gamma ray burst. And we know they are associated to the collapse of massive stars. And then there is at least another class of events. You see the blue distribution. These are short duration gamma ray bursts, which we usually define as those lasting less than 2 seconds. And this, we know now, at least some of these events are produced by the mergers of 2 neutron stars. And the reason gamma ray bursts are so interesting and we want to observe them is because they're really bright, extreme phenomena that we can use to explore our universe. So from the local universe up to a few tenths of megaparsec from us to the very distant universe. And you can see this in the figure on the right, where you see the luminosity of gamma ray bursts as a function of redshift. So you see that these events can release a very high luminosity, so a very large amount of energy in a very short time scale. And for this reason, we are able to detect them up to redshift 8 or 9 or even above, we hope in the future. So they're really important beacon to illuminate a universe that is otherwise dark to us most of the time. So the GRB field is, is now mature, but we still have a lot of new results. In particular, in the last year, there were a lot of Nature papers dedicated to new results in the GRB field that I decided to briefly highlight at the beginning of this talk. What you see here is this amazing detection of gamma ray bursts at very high energies. This was reported by the MAGIC collaboration and the HESS collaboration. They independently found evidence of a very high energy emission into gamma ray burst. And what you see on the left, this is the temporal evolution of the very high energy emission detected by MAGIC in 2019. And you see that photons up to 1 TeV were detected for several hundred seconds after the main gamma ray burst. And so the energy involved are really high. This was a really extremely energetic event. And you see on the right, the spectral energy distribution of this event. You see that the lower energy part of the spectrum, so everything that goes X-ray to hard X-ray up to the JV range, can mostly be explained by a synchrotron emission model. But to explain really this very high energy emission, it was suggested that we need an additional component, which might be, for example, inverse Compton. So this was really the first observational evidence for this new component in gamma ray burst. But it was not the only result exciting result we had in the past years. Here I wanted to highlight two more results that are connected to the GRB, to the link between GRB and supernova. One is, as you see on your left, there was this claim of a thermal component seen in the spectra of a nearby long duration gamma ray burst. So what this group did, it took very early spectra of the GRB and its supernova. And you can see in the plot right here, they see the emergence of an additional component, and they explain this as a cocoon of slowly moving material that is surrounding the GRB main outflow. And another interesting result, always related to supernova, is not observational, was theoretical. And so what you see on your left, this is the prediction of infrared emission from supernova produced with a gamma ray burst, what we usually call in the field collapsers, because they're different from standard core collapse supernova. They're really highly rotating massive stars that we think produce this type of energetic explosions. And so it was suggested that in the aftermath of the collapsar explosions, there might be the physical process so extreme to start the R process nucleosynthesis. So this could be actually the main sources of heavy metals. And one way to see this observationally would be to look at the infrared emission of GRB supernovae at very late time. So very interestingly, although this field has been studied for, I would say, 2 decades, most of the studies were really focused in the optical domain. So the constraints that we have on the infrared emission are not sufficient enough to really constrain this model. So this is something that in the future, especially with the James Webb Telescope, would be very interesting to test and see whether GRB could be really the main source of heavy metals. But the main focus of my talk is going to be the connection between gamma ray burst and compact binary mergers. Well, the reason for that is also that looking at the Chandra cycle 22 approved proposals, I basically realized that all the Chandra proposals approved were connected somehow to short gamma ray bursts and neutron star mergers. So it looks like this is the field where Chandra is giving like the biggest contribution. So the connection between gamma ray burst and neutron star mergers is, is a very long-lasting idea. What you see here are the possible pathways leading to the formation of a relativistic jet and therefore a GRBs. We may have two neutron stars spiraling into each other and then finally forming either a very massive neutron star or an accretive black hole. And this accreting black hole may power a relativistic jet. The other option that has not been tested yet would be to have a neutron star that is tidally disrupted by a black hole. And so this would create, again, a similar accretion disk capable of producing the observed gamma ray emission. So our study of this has been also in the years confirmed by the idea that short GRBs are indeed collimated into jet. So this confirmed the idea that we were seeing emission from a very narrow jet formed by the accreting black hole. This is an example of how we measure these jets. What you see here is the typical afterglow of a short duration gamma ray burst at different wavelengths, so radio, optical, and X-ray. So this is how usually the afterglow of a gamma ray burst looks like. You see it's more or less a rapidly fading source. And after, I would say, one or a few days, we see that at all wavelengths, the observed light starts to decrease very rapidly. And so we interpret this as the sign of a collimated geometry. And so this has been, I think, one of the most long-lasting programs that has been carried out with Chandra, because as you can see in X-rays, the afterglow of a short gamma ray burst fades really quickly. So with Swift, we cannot detect them for more than a couple of days usually. And so using Chandra as a facility is critical to really track the X-ray evolution up to very late times. And so we have so far a few of these examples in the sample of short gamma ray burst, and they all tend to confirm that these events are produced by a relativistic jet. But as you can see, the information that we had up to a couple of years ago was really limited to a few points on a light curve. And with this, we could say, okay, there is a jet, it's quite narrow, but we were missing a lot of information that was revealed to us a couple of years ago when there was the joint detection of a short gamma ray burst with a gravitational wave event. And so that this really represented for us a major leap forward in our understanding of these events. So what you see here is our standard model of a gamma ray burst emission. You see at the center, there is this central engine. It might be a black hole, it might be a neutron star, we don't know yet. But we know that this central engine that is formed after the collision is powering this very fast moving outflow. And these very fast moving outflows are responsible for the gamma ray emission that we see at the beginning. And after, is also responsible for the broadband afterglow emission. So when this very powerful outflow interacts with the surrounding medium, it creates this multi-wavelength radiation that is visible at X-ray, radio, and optical wavelengths. So what you see here are the three different detection of the GW afterglow in 2017. But what this detection also revealed to us in amazing details was the existence of another outflow that is not as fast as the jet, but is still very important. And this outflow is revealed in the very first few days after the merger. It produces a very bright optical and infrared emission that we call kilonova. So I will start showing the GW afterglow. And as you can see, if you compare it with the previous afterglow that I showed to you, this is completely different. This is not fading. Instead, we see its emission is rising in time, and then it's kind of plateauing for a few months, and then it's rapidly fading away. So this is very different from the typical afterglow that we see in short duration gamma ray burst. And one thing is we have a lot of evidence now that this was powered by a relativistic jet. Because this was so close to us, it was possible to carry out high resolution radio imaging of the source. And you see an example here. What you see in red is the radio emission after a few months. And the black contours is the same radio emission, but several months later. And you see that the centroid of the radio image is moving, and this movement implies a superluminant motion, which is a clear indication of relativistic jet. From the X-ray side, we also found evidence for a relativistic jet by monitoring the temporal evolution. You see this in the right panel. And you see that the temporal evolution of the observed flux was declining at a very fast rate. And when you compare this rate with the rate expected from other models, which do not produce a relativistic jet, then you see that they're mostly inconsistent. So although there was some ambiguity at the beginning, these late time observations were really critical to identify the emergence of a relativistic jet from a neutron star merger. And so this is the picture, I think, that most of us agree upon at this moment. So we agree that this incredible event, this collision of neutron stars, created a relativistic jet that you see here in orange. And this confirmed our long-standing model of short duration gamma ray burst. But we also think that in addition to this, there is some other material. Some people call it the structure of the jet. Some people call it a cocoon surrounding the jet. But we all agree that there is some sort of envelope surrounding the relativistic core that you see here in blue. And when we observe GW170817, we think that this blue envelope is indeed what we saw at the beginning. So we didn't see the relativistic core because it was not directed toward our line of sight, but we probably saw the lateral wings of the jet. And this would explain all the unusual properties of this gamma ray burst, including its very oddly looking afterglow, as well as its low luminosity gamma rays. And this is the fact of the viewing angle. So what I'm showing here is the very same GRB afterglow as a function of different viewing angle. So if you are looking straight along the jet, you actually see a fading afterglow that you see here, which is similar to the garden variety afterglows that we observe with Swift. However, when you move far from the jet axis, you see the light curve of the afterglow is changing dramatically. Not only is getting delayed by several days, but is also getting fainter and fainter. And so you see that with Swift, basically, we can only detect these afterglows only if they're very close to the jet axis, something like less than 10 degrees. And in the case of GW17 or 817, we were really lucky because it was within the window of sensitivity of Chandra, which is about to 40, I would say 40, 50 degrees from the jet axis. But if the viewing angle is even larger, then even Chandra would miss a similar explosion. And so in order to really grasp the full range of afterglows, of axis afterglow from neutron star mergers, then we would need the next generation of X-ray emission. So we would need a factor of 10 increase in sensitivity at least, which is what we expect to have with Athena, for example. So this is another work that look for off-axis X-ray afterglows. So after we saw GW17 or 817, a natural question was whether we had observed anything like this before. Because if this is a standard short duration gamma ray burst, then we should have seen something similar in 15 years of Swift mission. So in our search, we found only one possible event that looks similar to GW17 or 817. You see on the right, the X-ray light curve of short duration gamma ray burst in gray. And you see in blue how 17 or 817 really differs from them because it's delayed and its peak is a late time. And so we found that this event 150101b could have been a possible analogs of 17 or 817 that we just missed because we still did not have in mind the good picture of how the off-axis emission should look like. And here is an update on 17 or 817 as observed by Chandra up to 6 months ago. I think that was the last observation. What you see at the center, this is the field, the X-ray field of GW17 or 817. You see at the center, there was this bright nucleus. So having Chandra was really critical because all the other X-ray instruments were not capable of resolving the emission of the afterglow from the nucleus. And you see in the timestamps, you see the evolution of the X-ray emission from the first detection at 9 days, all the way to the peak at 160 days up to March 2020, where it was still detected. So a possibility looking forward, as you see, is that now that the emission from the jet is fading away, and in all our models, we expect that the jet should become not detectable very soon. This opens the possibility of detecting novel components. And this is a prediction of, for example, seeing X-ray emission from the kilonova ejecta. We know that there were kilonova ejecta because we saw the kilonova. So we know that there was this large amount of merger ejecta moving at very high speed, something like 20–30% the speed of light. And indeed, what we show here are the predictions on the observed X-ray emission based on what we know of the kilonova. And there is a reasonable region of the parameter space for which the X-ray emission is going to rebrighten in the next few years. So this is definitely looking forward, a field where continued Chandra observation of this GW counterpart could really discover new components that were not observed so far. And so here I show recent results of a similar search for this kilonova afterglow, but it was carried out in the radio band. And actually there were 4 different papers on this subject that were presented in the last few months. And what you see in these lines are, these are the prediction for the kilonova afterglow in the radio, and the upper limits are derived from the sample of short gamma ray burst observed by Swift.
3 minutes.
Okay, and you see that except in these 2 cases where the energy is really high, so we can exclude with the cosmological sample, we can exclude some of the high energy models, which imply, for example, a long-lived magnetar. But for more typical energy of the order of 10 to the 51, the cosmological sample is really not sensitive to this model. So having these GW counterparts very close to us is going to be critical to for the search of this exotic kilonova afterglow in the future. So to conclude, I wanted to update you on the search for kilonova in short gamma ray burst. This is the first kilonova detected, candidate kilonova detected in 2013. After that, there were a few attempts to detect new candidates. Here is one that was proposed by 2 different teams. So at least we agree that there is some kilonova signal in there. And in this, I just wanted to point out that although the kilonova that you see here in the infrared light curve on the top, you see this little bump of infrared emission that we interpret as the emergence of a bright kilonova. But this was initially missed by simply analyzing the infrared data. And so for this particular case, we found out that having the late time X-ray to constrain the afterglow behavior was really critical to predict the afterglow evolution in the infrared, which was very different from the observation. So this joint X-ray infrared campaign was really critical to identify the kilonova bump that you see happens at 2-3 days after the merger. So for typical short GRBs, this is very much the same time scale where the afterglow is bright. So it's going to be very difficult to distinguish afterglow and kilonova unless you have a very good multi-wavelength coverage. And I wanted to conclude with this example, which happened very recently. So this is a GRB detected in May at a redshift 0.5. And there were Chandra observations that were critical because there was another X-ray source in the field of view. So the Chandra accuracy was critical to resolve the X-ray afterglow from the contaminating source. And also in this case, there is the detection of a very red source a few days after the GRB. This is consistent with a kilonova, but also with an afterglow. So this is 2 different models interpreting the broadband emission either as pure afterglow on the left and as an afterglow with a kilonova bump on the right. And unfortunately, we found in this case, the 2 options are really difficult to distinguish from one another. So the search for kilonova really requires multi-wavelength coverage, and hopefully in the future with the James Webb Telescope, extending the infrared coverage will really help to break the degeneracy between the models. And so I will leave you with the summary. So even if I focused on short duration gamma ray bursts and neutron star mergers, I would like to say that the whole field of gamma ray burst is still exciting. And every year we have new unexpected discoveries. This year was from very high energy emission, as well as possible cocoon from supernovae. In the field of short gamma ray burst and neutron star mergers, I would say that X-rays can give us unique insights, especially on the afterglow component. And so this is very important, not only to really study the jet coming out of these mergers, but as I discussed, is really critical to search for kilonova and distinguish and break the degeneracy between the models. And looking forward, I think late time observation of gravitational wave counterpart could help discover us further components of the mission that are not connected with the standard afterglow. Thank you.
Thank you for the excellent talk. We have a couple of questions from our attendees. So 2 questions that are somewhat related from Agniva Roy Chowdhury and from Dr. Pranav Ghosh. What are the relevant physical parameters you use to model the effect of viewing angle on flux evolution? And are there any degeneracies in that? And then the similar question is the degeneracy between inferred viewing angle and jet structure profile. Has there been any further progress in breaking this degeneracy?
Okay, let me answer the last one. So there is indeed, I think we all agree that there is a structured jet, but there are clearly different models to describe this structure. And with the observations we have with basically this one event, I don't think we can really break the degeneracy. I would say this is something that could be better constrained by having more GW counterparts. And I think having a larger sample of events, even the rate of events that we are going to detect depends on the profile of the jet. So I think this is something that will require a larger sample of similar events. We cannot do it, at least we assume a profile, but we do not claim it's the unique profile that is consistent with the data. So that, I think, answers one question.
And the other question is about what degeneracies are there when you're modeling the viewing angle and the flux evolution?
So if we use the flux evolution alone, I think there is a degeneracy between the viewing angle and the opening angle of the jet. There are other degeneracy that are intrinsic to the afterglow model, but I think when we talk about structured jet, really this viewing angle, what we can really constrain is the ratio between the viewing angle and the opening angle. Now, in this particular case, we also have gravitational wave information and the centroid motion of the radio. And so if we combine all this information together, then we can break this degeneracy. And so I would say we can break the degeneracy in the viewing angle. But if we just use the temporal profile, we cannot.
And then this question is from Lenny Saad. I recall seeing theoretical models that found the neutron star, due to its density, when tidally disrupted by a stellar black hole, would mostly be absorbed by the black hole, more so than, say, a regular star disrupted by a supermassive black hole. Would these sorts of gamma ray bursts be fainter than those caused by neutron star mergers?
She's right, because we think that in a large number of events, for a wide range of conditions, the neutron star is just going to be falling into the black hole with no signal. So is it possible that most neutron star black hole collision would not result in an electromagnetic signal, or maybe in something very faint? But when the neutron star is tidally disrupted, actually the simulation show that a very massive disk is formed and a large amount of ejecta are also released into the outer medium. So I think at this moment, if the disruption of the neutron star is successful, I think we expect a signal that is as bright as what we see in neutron star collisions.
Great. If we have no more questions, I'd like to ask a question about the very late time observations that you showed us the plot where you're going to have a rebrightening. And it looks like 10 years is what you need to actually, because based on the errors that you see for the fluxes in the diagram you showed us, it looks like 10 years is when you'll really be able to distinguish between those different cases.
Well, it depends on what we want to do. I mean, if we want to distinguish between the different profiles, yes, this is going to be a very long-term effort. But if we really want to, detect and be sure that there is something else, I don't think it's gonna. I think it's gonna take maybe a few years. Maybe a couple, because the jet emission is really supposed to fade fast. So if we keep seeing X-ray emission for, let's say, 2 more years, at least we can say that there is something else beyond the jet. To say what, to distinguish the different models and place constraint on the different profiles, it might take a very long time. But even knowing that there is something else there, I think would have a very high impact on, even on the way we search for gravitational wave counterparts. So this is a totally new counterpart that we have never seen before.
Excellent. Great. That's all the time we have for your Q&A. Thank you again for an excellent talk. Those are all really good questions from everyone. Thank you. Will our next speakers start preparing their slides? Our next speaker is Alicia Rouco Escorial, and coming from CIERA and Northwestern University, and they will talk to us about the X-ray afterglow and host galaxy of the unusual gamma ray burst 1804-18A.
Thank you, Rodolfo, and hello, everyone. My name is Alicia Rouco Escorial, and as he said, I am a postdoc in Wenfrey Fong's group at CIERA Northwestern University. So before starting, I would like to thank the Chandra Organization Committee for giving me the opportunity of talking about GRB 1804-18A. So let's start with a little bit of the introduction, although Eleonora already did a very good job introducing the main concepts of GRBs. But I would like just to underline that GRBs can be divided in 2 classes, short and long GRBs. And short GRBs, their duration is nominally less than 2 seconds. They are less energetic and they appear or occur in lower density environments. And thanks to the detection of the gravitational wave event 1708-17A and its emission in gamma rays, we got to prove that one of the channels of producing short GRBs are double neutron star mergers. On the other hand, we have long GRBs, which they have the duration of larger than 2 seconds. They are more energetic and they appear in higher density environments because we know that the progenitors are the death of massive stars, since they are detected in supernovae type 1c. So as you can see here, we have the distribution in duration of short and long families, and in between they overlap. And remember this because it will be important for the rest of the talk. So when we have 2 neutron stars and they merge, we see the prompt emission in gamma rays. And if we are lucky enough of observing this emission on the line of sight, we see that this emission comes in a very collimated and relativistic way, also outflow, called jet. And its bulk Lorentz factor is inversely proportional to the half opening angle. And as the Lorentz factor decreases in time because the jet interacts with the medium, at some point it becomes equal to the inverse of the half opening angle. So how we see this, as Eleonora already explained, is that in the decay in the afterglow X-ray light curve, at some point we see a change in the in the slope, and it becomes steepened. And we call this moment the time of the jet break. So knowing this time, the energetics of the GRB and the circumambulance density, we got to know the angle of the jet, and we can infer the distribution of jets for GRBs, and especially in the case of short GRBs, we can infer the rate of these events and therefore the rate of mergers of neutron stars in the universe. But let's focus on 1804-18A. This GRB was monitored and followed in the high energies by Fermi, Swift, and Chandra, and from ground-based telescopes, UKIR, MMT, and Gemini, in between one of them. So I'm going to present or reanalyze data of Fermi and BAT, Swift BAT. So from Swift BAT, we got a duration for this GRB of 1.9 seconds, and from Fermi GBM, we got 2.5 seconds. So this leaves us in an ambiguous case, because if this GRB is a short GRB, then it has a longer duration than expected, and also the hardness is softer than usual for a short GRB. And if it is long, then it's one of the shortest. So we plot all the Fermi GBM burst, hardness versus the time duration. And as you can see here, we see the short and long GRBs, and we place our GRB. And it falls in between both families. And just for reference, we plot also 170817, which is softer, but it falls also in the same place. So having into account the distribution in time for both families and in hardness, we can draw a probability for GRB 1804-18 to be like short, and we got a probability of 60%. So this leaves us like that we may say that this GRB is short, even though there is this discrepancy maybe in the time duration. So now I'm going to talk a little bit about the X-rays of this GRB. So at the beginning, this GRB was monitored by Swift. So we can see that at early times, it saw a decay in the flux. But after that, it entered in a plateau kind of phase. And this is a very weird thing for a short GRB behavior. So we inspected our first Chandra observation, that it was obtained 7 days after the pulse trigger. And we detected the afterglow there in the blue, you see. But within the source region extraction, we see that there is an extra source in X-rays. And obviously, if we go to our Swift data, this source is there. So all the data that we have right now, it has a contribution of this contaminating source. But thanks to the data that we got from Chandra, we got into account the flux of the contaminating source, we subtracted it, and then we could get the real unabsorbed flux of the afterglow. So if we plot all our data, we get the Swift afterglow decay in X-rays. As you can see, the last point is under the contamination source flux level. And if we add our data from Chandra, we see that the afterglow decay, sorry, the afterglow decay light curve is well modeled by a single power law decay. This means that we don't detect a jet break up to 39 days, and then this means that we cannot get a value for the opening angle of the jet, but we can place a lower limit for it. And just to underline that this GRB is one of the few with lead time at least up to the 30 days after the trigger of the burst. So just to put 1804-18 in the context of the Swift GRBs, we select those Swift GRBs with non-redshifts, and for the short GRBs, we took into account also the late time observations of XMM and Chandra, and we plot the luminosity versus the rest frame time. And we selected two slices of time, one, let's say, early times at 10 to the 4 seconds, and other one at 10 to the 6 seconds, which will be the late time. And we place our GRB at two different redshifts, 1 and 1.5, and I will let you know why these two numbers in a few seconds. And if we place, as I said, our GRB, we see that if it is placed at redshift 1, it's closer to the peak of short GRBs at early times. But if it is at 1.5, it starts being part of the long GRB distribution. However, at late times, we see that anyway, it doesn't matter at what redshift is, we see that it's embedded by the long distribution population. So this can be because of two reasons. One is maybe this GRB is long, but we believe that it cannot be possible since we got this probability from our Fermi GBM data. The other reason is that maybe we have a bias here, and it's because we don't have late monitoring of GRBs at late times, and we need more data for populate this part of the plot. So let's talk a little bit more about the afterglow monitoring in the optical. So here I show you the monitoring of the afterglow done by Gemini. But I would like to underline that after 288 days, we detect a faint host galaxy in the R, in the Y, and Z filters. And thanks to this detection, we could place a constraint in the redshift of the host galaxy and also the event. So it is between 1 and 1.5 in redshift, and also we could place a limit in the luminosity of the host galaxy. But if we put all together our results and already the published results in the past, at early times, this work was published by Becerra et al. In 2019. This GRB is the first time that we detect a reverse shock in the optical and also at so early times. And this is very difficult because these GRBs evolve very quick in time. And now if we put into context our data with all the data that we had, we see that this afterglow decay is also well modeled by a single power law, and we don't detect, again, a jet break, neither in the optical and nor in the near infrared. So let's put together our results from the optical and near infrared with the X-rays. And then we see we can infer some values for the energetics, the circumburst density, and opening angle of the jet. Sadly, the frequency of the optical and the X-rays, they fall in the same spectral segment and is under the cooling frequency. So this means that we have a degenerated parameter space for the energy and the density. However, we can place at least the lower limits for the jet opening angle. So if our GRB is at redshift 1, this opening angle is going to be larger than 9.9 degrees. And if it is at 1.5, the opening angle at least is larger than 8.7. And we think that this is, again, a reason to think that it's a short GRB, because long GRBs in general show narrower opening angles.
3 minutes.
Just for finalize the talk, I leave you with my conclusions. Thanks to Chandra, we detected the short GRB, the GRB 180418 at 239 days. Thanks to the accuracy and high resolution, we were able to have an enhanced position of the GRB and also detect the contaminating source that was giving us a ground flux. And accounting for that flux, we got an accurate X-ray afterglow that led us to put better constraints in the opening angle of this GRB. And just to leave this note, as also Eleonora said, and most of the speakers in these sessions, that Chandra is essential for performing the monitoring at late times, especially for characterize and investigate the behavior, as you can see in this region at late times for the afterglow of short or potentially short GRBs. Thank you very much for your time and for your attention.
Thank you, Alicia, for that excellent talk. If we have any questions from the attendees, please enter them into the Q&A box. If not, we have a question from Agniva Rauchaudhuri. Do you have any new clues as to the physical emission mechanism that produces these X-rays?
Well, I think right now it's just the afterglow of the jet that is when it's reacting like interacting with a medium. But right now we are just having the the fireball modeling for explaining all this data that we have. We are not having any better constraints for the mechanisms.
Any other additional questions? I have a question about the late time monitoring.
Mm-hmm.
Has there been any attempt to go looking for serendipitous observations of early AGBs from early in Swift's mission, but although maybe we might be stepping on Brendan's toes.
Yep.
Or I'm sorry,
What do you mean?
Simone's
Sorry.
toes.
Sorry?
So if we look at X-ray bursts, gamma ray bursts that were detected, like, let's say years ago, looking for observations of them, late time observations of them in the archives, to look and see if any of them are still detected or brightening.
Yeah, that is a good question. I also bring out this topic. I would like to try this, but basically we expect that if it is like a short GRB, we don't detect any X-rays, especially if it is now, and these are from some years ago. But anyway, for example, like I don't remember which one was. I thought, okay, we can maybe try an X-ray, but the justification for observing this is going to be very hard because as we see, most of the modeling for the X-rays decays. So, but I would like to try it. So
it's faint.
Yeah, it faints.
And is the emission? Do you have any idea of where the emission is in the X-ray spectrum? Is it hard or soft?
For short GRBs, it should be in the hard. Like if we go, sorry, I'm going to come here. Sorry. Yeah, we expect hard emission. This is gamma rays, but also in the X-rays.
Okay.
Yeah.
Excellent. Thank you again. Thank you all for the questions. Let's go on to our next speaker. Brendan, I'll ask you to start sharing your slides. Our next speaker is Brendan O'Connor from George Washington University, University of Maryland College Park, and NASA-Goddard Space Flight Center, talking to us about the merger environments of short gamma ray burst.
Yeah, hi everyone. So I'm a fourth year graduate student at the George Washington University, and today I'll be talking to you about the merger environments of short duration gamma ray bursts. So the motivation for this work is, are there truly hostless short GRBs? So I'd like to highlight that 20% of well-localized short GRBs lack a strong host galaxy association. And in particular, I'd like to discuss 06-1201. We see on the right that this short GRB has a very accurate localization, shown by the red circle, and that it's very nearby to this galaxy referred to as G2, which is about 1.5 arc seconds away. But if we look at a larger view of the region of the short GRB, which is this red cross, we see that there's a larger galaxy that's much more nearby and much brighter, referred to as G1. And the question is, which is the true galaxy that this short GRB was born in? And although G1 is much further away from the GRB position, the probability that these galaxies are associated with the GRB are equivalent. And that makes it very difficult to tell which one's the correct host. This has implications for what is the redshift of the short GRB and also for the intrinsic offset distribution for short GRBs. If we look on the left, we'll see this plot of the cumulative distribution function for short GRBs in red. And we see that 20% of them are occurring at large distances of like 10 kiloparsecs away from their host. So these galaxies where we don't know the host association are referred to as observationally hostless. And that just means that based on our observations, there's multiple galaxies with similar probabilities, or there's very deep limits on an underlying host. So I'd like to distinguish between observationally and physically hostless, which is a definition we use in this work, is we have the formation of the neutron star binary, and when the second neutron star is formed, it has a supernova explosion that ejects some mass, and this can change the center of velocity of the system and move this neutron star to a very large distance from its galaxy. So this delay time between the formation of the neutron star binary and its eventual merger due to gravitational waves allows for this system to move to very large distances. A schematic is shown on the right, where we see if we have an initially circular orbit, and then this second supernova occurs, we get a very highly eccentric orbit. And this orbit would be for these observationally hostless short GRBs, where it's a highly eccentric orbit, and the neutron star binary can eventually merge at a much larger distance from where it formed, but it's still going to be contained within the galaxy. That's what we refer to as observationally hostless. There's no host galaxy, but we believe this short GRB still occurred within its galaxy's confines. The other option is if the natal kick is very, very large, that this short GRB can get in a hyperbolic orbit and actually escape its host galaxy, and eventually this binary system will merge in the intergalactic medium and not within the density of its galaxy. And at these large offsets, we expect the density to be very low. So the question is, how can we relate the density of short GRBs to the positions on the sky we see them occur from their birth galaxy? So how do we get very large offsets? And what's the evidence for large offsets in the literature? So isolated pulsars are observed to have very large natal kick velocities on the order of hundreds of kilometers per second. And following a very large natal kick like this and a long delay time, which can be up to 10 billion years, 1 billion to 10 billion years, we can get to a very large distance from the galaxy, which we expect to have low densities. And this is why observationally hostless short GRBs, like I said, make up the 20% of the short GRB population at large distances from their hosts, have been interpreted to still be plausible. And especially when we consider that in highly eccentric orbits that are still bound to their birth galaxy, it's more likely that these systems are going to merge at their maximum radius just due to Keplerian dynamics. They're move more slowly when they're further away from the center of gravity, and they spend more of their lifetime there. But there is some evidence to the contrary, because low natal kick velocities and short time delays have been found in galactic binary neutron star systems. So there is a matter of debate as to, how large of a distance can we actually theoretically expect these systems to occur, and whether or not that agrees with the offset distribution. So this has been, highlighted by Nora, but the GRB afterglow emission is how we can constrain the density. And how that occurs is we have the binary neutron star system. It merges and a relativistic jet is launched. This jet is initially moving at a near constant speed, but eventually it piles up enough material in front of it and begins to slow down. This is what we normally refer to as the afterglow phase, and we see a declining light curve when the jet has decelerated. And we can use the afterglow to determine the density. So I'd like to highlight a correlation between the X-ray flux observed at 11 hours and the gamma ray fluence of the initial short GRB. So the correlation is shown on the right, where we have on the y-axis the flux and the x-axis the fluence. So the fluence is independent of the density, but the X-ray flux is proportional to the density to the 1/2 power. And we found in my work that this correlation does not require that short GRBs have low densities. And in fact, a similar correlation is observed in long GRBs in the literature, and has potentially been interpreted as evidence that long and short GRBs could have similar environments. And we know that long GRBs occur in very dense environments because they're formed by collapsars, and those must occur and form in very dense star-forming regions. So there is some evidence, although it's not super substantial, at this point, that these long and short GRBs could have similar environments. And this is something we wanted to hope quantify and look into further. So the way we did this was by taking a sample of 52 short GRBs detected by the Swift Observatory. 19 of these have known redshift, and we use the early X-ray afterglow light curves. So if we look on the left, there's a schematic of these typical light curves seen for short GRBs, which we've seen in some of the other talks. But what we don't see in the other talks is the deceleration phase of the jet, which is this blue shaded region highlighted as unobserved. This is something that's actually observed in long GRBs. And so we know the physics of this very well. We have the blast wave, it's been launched, it's moving very fast at a near constant speed, and the flux is increasing until the point where the jet begins to decelerate, which is the peak of the X-ray light curve. And if we take an upper limit on the peak time and a lower limit on the peak X-ray flux for these short GRBs, as these are proportional to the density, we can invert them and solve for lower limits on the density, which is shown on the right. This purple curve is a cumulative distribution function of lower limits on density for bursts with redshift determination in our sample. And as such, the allowed densities for each of these GRBs are to the right of this curve. So we see that very low density environments are excluded, and that actually less than 16% can occur in densities less than 10 to the minus 4 atoms per centimeter cubed, which is the density we interpret through our calculations as the density at the galaxy's edge of a typical short GRB galaxy. And within the confines of this talk, I can't really get into how that's calculated, but I'd be happy to answer questions. So if 10 to the minus 4 is the density at the edge of a short GRB galaxy, then less than 16% of this sample can actually be physically hostless and have escaped its host galaxy.
3 minutes.
So I'd like to discuss how this, the implications for hostless short GRBs, because we're saying that less than 16% can occur, less than 16% of short GRBs, which we know, haven't been referred to as hostless, cannot be, escaping their birth galaxy. But how do these density limits apply to those GRBs which have been referred to as hostless in the literature? And that's what this plot is showing us. So on the y-axis, we have the lower limits on density, and on the x-axis, we have the redshift. So if we look at this magenta curve for 06-1201, essentially what we're doing is calculating the density, the lower limit on density for this short GRB as a function of the redshift, and seeing that at no redshift does it go below 10 to the minus 4. And in fact, 4 out of 5 of these observationally hostless events, which in the literature have said to not have a very strong host-galaxy association, cannot be physically hostless because their densities are higher than what we expect to be in the intergalactic medium. For the one event, the red curve here, 091109b, we see that if we take the typical short GRB redshift observed, 0.5 to 0.9, somewhere in that range, depending on the sample and the paper you look at, we see that this event actually is constrained to be higher than 10 to the minus 4, and we interpret this to mean that none of these events which have been deemed hostless actually occurred outside of their birth galaxies, and might actually have occurred in higher redshift galaxies at smaller offsets to the GRB position, missed by the deep observations. In summary, less than 16% can actually be physically hostless, and the main takeaway is that short GRBs must occur in higher density environments than previously predicted. None of them can occur at very low densities consistent with the intergalactic medium. I'd like to highlight how Chandra can help. So Chandra can provide a very accurate localization of the X-ray afterglow, which allows us to identify better host associations for a larger number of short GRBs. And this is because the optical afterglows for short GRBs are only detected in about 40% of the sample. And typically the well-localized events come from these optical detections. But if we can increase the number of localized X-ray events, that's a larger sample for which we can do these types of statistics. And that has implications for the redshift distribution of short GRBs, which in turn tells us the delay time distribution, the offsets, which tells us how these natal kicks work. And in turn, these quantities can help us determine the expected rate of gravitational wave events by LIGO Virgo. Another new telescope that's coming soon is the James Webb Space Telescope. And as I said, it's possible that some of these observationally hostless events are occurring in higher redshift galaxies that are just very faint. Well, James Webb will provide deeper constraints, especially in the infrared, which traces most of the stellar mass and can help constrain the actual maximum mass of a galaxy that could have been missed by these observations if in fact James Webb does not continue to uncover, these host galaxies and they're actually very faint. This would be interesting because it would tell us whether or not these potential high redshift short GRBs have to occur in faint dwarf galaxies or whether or not they can still be missed in galaxies at, a typical short GRB stellar mass. And that will be interesting for the environments of short GRBs. So yeah, thank you. I'd like to answer any questions now.
Thank you, Brendan. We have two questions. The first question is from Solon Ballman. How large is the large separation, the large offsets for these neutron stars from natal kicks, and are there models?
Yes, so there are models. I can go back to that slide. So the offsets are in kiloparsecs here, not arc seconds. So this is a physical offset, which, if you take the redshift of the GRB and the arc seconds offset, you can compute this physical offset. These are actually lower limits on the true physical offset because these are projected onto the sky and not the true 3D distance. So in red, we have the short GRBs, and we see that 20% of them are occurring at larger distances, out to about 75 kiloparsecs is the largest one right now. And these neutron star merger models from, I believe, Bloom et al. 1999 are predictions based on the natal kick velocities inferred from isolated pulsars, which may be different to galactic neutron stars. So we see that if we take these very large natal kick velocities, we will find distributions theoretically that agree with observations. But if the natal kick velocities are actually much smaller, like they are observed in galactic neutron star systems, then these theoretical models may not agree with the observed offsets. And that's an upcoming work that I'm working on now, but I don't have the results to present at this time.
Great. Thanks a lot, Brendan. You have two more questions in the Q&A that we don't have time for you to answer live at this moment. So if you want to type responses to them, please feel free to. I'll ask our next speaker to start sharing their slides.
Thank you.
Our next speaker is Simone Dichiara from the University of Maryland and NASA-Goddard, who will talk to us about a search for short gamma ray bursts within 200 megaparsecs with the Neil Gehrels Swift Observatory.
Okay, can you hear me?
Yes, I can hear you. Your
Thank
slides
you.
are,
Thanks.
That's better, good.
All right, thanks, Rodolfo. Thanks to the other speakers for very interesting talks. My work is mainly focused on the search of nearby off-axis short GRBs. As well introduced by Eleonora before, off-axis short GRBs are characterized by faint afterglow with delayed onset and late time peak. In this figure, you can see a comparison between on-axis short GRBs, afterglow detected by Swift in gray, and the Chandra light curve of two known off-axis events, 1501-01b in red and 1708-17 in blue. As you can notice, they show a very different behavior. Off-axis afterglows are orders of magnitude fainter than the on-axis one, and very likely they would be missed by Swift X-ray observation, which are optimized to the detection of the early bright afterglow, like as observed for on-axis afterglow. And so the purpose of our work is oriented to answer the following question. Did we miss any off-axis event in the nearby universe in the past? In order to address this question, we consider the whole sample of short GRBs detected by Swift up to January 2019, which consists of about 130 events. And we selected the ones with no afterglow emission and ending up with a sample of 32 bursts. We then cross-matched the GRB localization with the catalog of nearby galaxies, and we found 4 possible matches with galaxies at distance less than 200 megaparsecs. This number is higher than the one expected from Chandra line. Though the number of events is low, this result suggests a possible real physical connection between these short GRBs and the local galaxies. So then we searched for possible associated kilonova for these 4 candidates. And here, unfortunately, we have no infrared observation available to constrain the red emission of the kilonova, but we use the optical limits that you see in the figure. And as you can, and we compare, you can see here the optical limits in absolute magnitude compared with light curve of a 17 kilonova, which was observed at a viewing angle of 25 degrees about. And also for comparison, we showed the kilonova, the light curve of a kilonova observed at 60 degrees viewing angle. And as you can see, we can rule out the presence of a bright optical kilonova like AT 2017 GFO, but we cannot exclude fainter events, probably observed at higher latitudes. And we also use our result to constrain to derive the all-sky rate of local short GRB, which we find to be 160, about 160 per gigaparsec square per year. It's in the orange region in the figure. You can see that this rate is much higher than the rate derived from cosmological observation of short GRBs, and it's more similar to the rate predicted for the binary intrastar merger provided by the LIGO-Virgo collaboration. And we also derived the detectable rate of local short GRB for Swift and Fermi, which is 0.16 events per year for Swift and 0.8 events per year for Fermi. And in conclusion, our results suggest that events like 17 or A17 are not frequent, and the number of gravitational wave GRB common detection with GRB will probably increase slowly in the future.
Thank you, Simone. Do we have any questions from the attendees? Please enter them into the Q&A. If I have a question, these were detectable by, you were using thresholds for Swift. Have you thought about the thresholds that eRosita might provide? It must be not as sensitive, I guess, in some parts of the sky.
Sorry, I didn't understand exactly the question.
What kind of impact might eRosita provide for detecting, for doing similar study like this and detecting these sources?
For example, here in this figure, I have the sensitivity limit of XRT. I'm not really aware about the sensitivity limit that would provide like eRosita, or which would probably but you can see like the flux, the average flux of axis events is typically, I mean, for the two that we have so far is like about 10 to the minus 14 to 10 to the minus 13 Hertz per centimeter square per second. So I don't know if Rosita will reach this sensitivity, probably would be able to detect like similar off-axis events.
Excellent. Thank you again. I'll ask our next speaker to start sharing their slides. Our next and final speaker of this session is Davide Lazzati from Oregon State University, who's going to talk to us about GW 170817, from merger to jet to outflow.
Good morning or good afternoon, wherever you are. And thank you everybody for having me here. So I'd like to take a little bit of a different approach to looking at GW 170817 as a gamma ray burst and as a theoretician, of course. And so I'm going to focus today a lot on the difference between what I call the jet and what I call the outflow, and that's right in the title. So there is a jet, who is the thing that is produced by the remnant of the merger, whatever it is. And then there is an outflow that is what produces the radiation we detect, and it's maybe 10 to the 13, 10 to the 14 centimeters farther away from where the jet is produced, and a lot of things going on in between. And so the key of understanding the message in this talk is to really think about these two things. There is something that is intrinsic to what the remnant of the merger has produced, and something else that sends us photons that we can interpret, and how we connect these two things. If I can change my slide, here we go. So we had a great introduction about gamma ray burst and a lot of talk about 170817. So I'm not going to spend a lot of time here. A few basic things. We know that the gamma ray photons arrived about 2 seconds, a little less, after the gravitational waves, which is a very important piece of information, and is the first time ever we have that gravitational wave trigger to let us know when the actual engine was created. And we've all seen this nice figure with the gravitational waves, and then the gamma rays coming a little later. We heard how the prompt emission, the gamma ray component of this burst, was greatly under energetic, probably 10,000 times to 100,000 times less energetic, at least along our line of sight, than typical short gamma ray burst. And we've heard also how the afterglow appeared very late and peaked even later. And here is one of the various realizations in which you see it was first detected about a week or so after the gravitational wave trigger, differently from other or previously observed afterglow. Instead of fading right away, it actually kept brightening until a few months later, when it eventually peaked and faded away. So from a certain point of view, it's a very unique event that presented us with a data set that was different from anything else that we'd seen before. On the other hand, though, it's fairly well behaved as a gamma ray burst. It's true the prompt emission is very under energetic, but it's also true that as long as we consider, and we'll see in a moment, a little more about cocoons, but if we, as Nora was saying earlier, if we allow the jet not to be a triangle, but to have some structure in the polar direction, then we can reproduce the energetics, the duration, all the characteristics of that gamma ray burst pulse. And here's actually, as you see, this blue line is a model based on photospheric emission from the cocoon, which is a fairly standard approach to modeling gamma ray burst, and it does a pretty good job. And the same can be said about the afterglow. As you see, I can draw a line through all the points using a model, which is the model that we've been using for modeling afterglow of gamma ray burst for 20 plus years now, with just a small modification of, instead of considering just one number for the energetics, to allow this number to be a function of the angle away from the jet. It doesn't have flares, it doesn't have variability on short time scale. As you see, the thick lines go through the color points pretty nicely. The reduced chi-square is order of 1. So it's unique, but it's just because we saw it from a unique position that made it unique. And again, what is the cocoon here? I have a simulation to show you. This is an hydrodynamic simulation of a gamma ray burst jet that we launch inside this blue hazy structure that is the ejector from the merger. And as you see it running, we see the jet coming up. It struggles at the beginning against the denser part of the ejector. Eventually it makes it out. And you can see all this bluish cigar-shaped structure, and that's what the cocoon is. And what the cocoon does is when the jet finally breaks out on the surface, it creates this mushroom-shaped structure. And so you see that stuff gets deflected. It doesn't only go out along the direction of the jet, but it branches out. And so even if we're looking at 30 degrees, which would be somewhere around here, there is still material moving in our direction. It's not the jet material, it's the cocoon material, but it's still relativistic, it's still hot, and it still produces radiation. It looks like in very similar ways. So what can we learn after we've done all these feats and they all seems good? Well, there's pros and cons in the success of this modified pre-existing theory of afterglow and gamma ray emission and gamma ray burst. One is that we can all high-five each other and say, yeah, we knew it, we can model it all. There is a drawback though, which I think is really important, and is that what we can model are the properties of the outflow. We can model how wide it was when it was outside of the merger region. We can model how fast it was moving, but that doesn't tell us really how it was born. And things that are really important for understanding how the merger physics work, even things like the equation of states of neutron stars, how the jet are produced, whether the engine was a black hole or a neutron star. All those things want to know what the properties of the jet were when it was created, not after it went through the interactions and it became an outflow. So can we do that? Can we look at the outflow and see, oh no, this came from this particular jet? No, unfortunately, it's a big fat orange no. What we can try to do is the opposite problem. We can start from different configuration of jets and ejecta, let them propagate and see what outflow they make. We can do it using numerical simulations, which give us a highly confidential, not confidential, we can have a high confidence that that gives us the right answer. Or we can do it with semi-analytical approaches, which are faster, but allegedly less accurate than numerical simulations. Do they work? Well, here is an example. So first, doing enough numerical simulations to really try to figure out what happened in 1708-17, it's impossible. Each of them takes a year-ish to run, and you would have to run hundreds or if not thousands. So this is what we can get from the semi-analytical approach. This is a model, thank you, in which we just input some characteristics of what we observed, the energy along the line of sight, the opening angle of the core of the jet, the total delay, the 1.75 seconds, and the fact that the Lorentz factor along the line of sight had to be small to explain that late emergence of the afterglow. And we took ejecta from general relativistic simulations. We feed all of these into a semi-analytic jet propagation model, and we start with jets with all possible properties, and then we only keep those that obey these 5 observations. And can we constrain the properties of the jet as it was launched? The outcome is a bit not as good as we would like, maybe, but we do get some outputs. And this is the corner plot of doom. So let me summarize it for you. We can, for example, look at this parameter eta, which is the Lorentz factor, which with the jet was launched, and is constrained to be fairly high, in the thousands, as we have always thought for gamma ray bursts, not surprising. We can look, this is a very good one. This is the, I hope you can see my cursor, otherwise when I say this, you're lost. So the one that says theta j, the third column from the left, is the angle with which the jet was injected, which turns out to be between 10 and 20 degrees. So fairly wide, wider than probably we might have anticipated, but not in the crazy land. Other important things, we can independently constrain the next column to the right, the line of sight, those famous 25-ish degrees at which the burst was observed. And as a safety check, we recovered that without constraining it in any way. And we can also look at this, the last one, the delta TMJ. That's the time between the merger and the time at which the jet was launched. And it turns out to be small. It's nowhere comparable to the 1.7 seconds. It's probably 0.1 or 0.2 seconds. So most of that 1.7 is actually propagation of the fireball. And I don't have time to show you this simulation, which is a bummer because it was a nice one. And now it has stopped my computer. Okay, let me go back to the conclusion slide. Okay, well, sorry, technology. Here we go. So great success with 1708-17 in modeling the gamma ray burst related stuff. But again, I think we really need to go from the outflow to the jet. Otherwise, we will only know about the gamma ray burst aspect and not the real physics questions, merger physics, nature of the remnant. I think the key is going to be to use numerical calculation to calibrate these semi-analytic tools and use them eventually to get to the properties at birth. And this is the first event, no long gamma ray burst ever, we've been able to do this job because we always see them down from the hole, and that's not the best. And let me finish with, we need more multi-messenger events. 1708-17, we squeeze it like a lemon, and now there's nothing left inside. Thank you very much.
Thank you, Davide, for the very interesting and entertaining talk. If you want to try to play the animation while we wait for questions, that's an option.
Sure.
It's just, I did notice, yeah, you were freezing a little bit. Yeah, let's watch that.
So this is a 3D simulation in which we took the ejecta from a merger simulation with all the overdensities, underdensities, velocities, ripples, and we drove a jet into it. The greenish stuff is the actual neutron star merger ejecta. They are expanding with the jet, and the jet is flaming through it. It's interesting how uneven is the propagation of the jet because of the roughness, how corrugated the ejecta are. And that's where the jet is finally making it out. And that's where we are with the calculation.
Nice. Here's a question from Lenny Saad. 2 questions. Would the jet expanding into a mushroom shape after exiting the ejecta occur in long gamma ray bursts as well? And now ask the second question after you've considered that one.
Yep. So the answer to the first question is yes. I think we haven't seen yet a long gamma ray burst from the side, and so we don't have the solid proof of that. But theoretically speaking, we do expect the same mushroom shape. Actually, we expect it even more pronounced because in long gamma ray burst, the jet has to fight against an entire mass of a star there's a whole star there, and here we are talking about neutron star ejecta that are the order of 1% of the mass of the sun. So much more mass, much bigger cocoon.
And the second question is, how are we observing the jet in the afterglow if it's expanding into a non-jet shape after breaking out?
So it still maintains a jet shape. What that simulation couldn't show is that there's still much more energy in that collimated internal core. So the structure becomes a jet with wings. It's not just a kind of uniform mushroom. So you can still see the jet because there is a higher energy density along the axis of that mushroom, in the stem of the mushroom, if you want.
Great. One last question from Solon Ballman. What about the composition? What difference does that produce in models? And did you see this in your results?
So the composition, there's two compositions we are interested in with. One is compositions in terms of different atoms, iron versus helium versus protons. It is expected that because these jets come out from regions that are hot enough to photodissociate almost every nucleus, they will be mainly made of protons. So I haven't explored any jets that are not that have a component of heavy ions. I know there are ways to put the heavy ions in there, even intrinsically from the engine or picked up from the ejector, but we haven't explored that. Something we're working on is about neutron content. And so when we compute the photospheric radius, the radius at which the flow becomes transparent and we get the gamma ray photons from there, whether there is a high percentage of neutrons or not will change things, because if you have more neutrons, you have less electrons, and electrons are those who provide the opacity. So we are exploring that, and we definitely get hotter but weaker transients when we consider neutron-rich outflows.
Great. Thanks a lot, Davide. Thanks a lot to all of our speakers. That was a very interesting session. I'd like to remind you all that on Thursday, our next session starts at 8 a.m. Eastern time, and it'll be on X-ray binaries. Thank you again for joining us. I hope you join us next time. Bye.